In this video, we'll learn about the structure of a p-channel MOSFET, or what we call a PMOS transistor. So we know the structure of an NMOS transistor. The structure of a PMOS transistor is exactly the same. However, all we need to do is reverse the polarity of the semiconductor, the different semiconductor regions in the NMOS transistor. So, for example, instead of using a p-type substrate in an NMOS, in a PMOS, we are going to use an n-type substrate. And instead of using heavily doped source and drain with n-type material, we're going to have the source and drain as heavily doped regions using p-type material. So p plus for the source and drain instead of n plus for the source and drain. And then we'll have the silicon dioxide, the gate electrode, and then we'll have metal contacts for the source and drain, and for the gate as well, of course. And then we have for the body as well, or the substrate contact. This is the gate. Now let's look at the on and off state, or specifically the off state of the PMOS and then the on state of the PMOS. So this is the structure of the PMOS shown at the lower left corner. Now, what happened here is typically the source terminal is going to be the terminal that has a higher voltage or higher potential than the drain terminal. So in an NMOS, that wasn't the case. In an NMOS, we said the terminal that in an NMOS, we said that the terminal that has the lower potential is going to be the source terminal. On the other hand, in a PMOS, we say we will have the terminal that has higher voltage or higher potential. It is going to be termed, or we're going to annotate it as the source terminal. And why is that the case? Well, as we're going to discuss the on state of the PMOS, we'll see that the conducting carriers for in a PMOS transistor is going to be the holes or positive charge. So the source of the positive charge will come from the terminal that has higher potential because it carries more positive charge. On the other hand, in an NMOS, the carriers are basically electrons. So the source terminal is the terminal that has lower potential than the drain terminal, and that's essentially where electrons are going to originate. Because remember, the current, essentially the electrons will flow from source to drain, while the current, since the current is annotated as the flow of the negative, the flow of the in the negative direction of the electron flow. So this is the current from right to left. However, the actual flow of electrons is from left to right. So source terminal is the terminal that has lower potential. In an NMOS, it's the source of electrons, while in a PMOS, the source terminal is the terminal that has higher voltage or higher potential because it is the source of positive charge. Now, let's first start, before going into the on state of the PMOS transistor and how the channel is formed, let's look at the off state. And here we're going to assume we have in the off state, the gate is shorted to the source. The source has a higher voltage than the drain. So, and we're going to call it V source drain instead of VDS, because the source is higher voltage, higher potential, is at higher potential than the drain. And in this case, we're going to connect the substrate to the terminal of higher potential, which is the source terminal. In an NMOS, we connect the P substrate to the terminal of lower potential, which is the source terminal in an NMOS. In a PMOS, the same thing, we connect the body terminal to the source terminal, but in this case, the source terminal is a terminal that has higher potential or higher voltage. So we have a positive, a positive voltage difference between the source and drain, and the gate is essentially shorted to the source terminal. So in this case, what we are going to find is we have a diode here between the P plus region and the N substrate, and another diode between the drain terminal and the substrate. Now, since we have a short circuit between the source and body, this diode we can ignore, and basically we can represent the transistor. If this is the source terminal and this is the drain terminal, what we have here, we have the anode terminal of this diode connected to the drain and the cathode terminal connected to the source. And so when we apply a positive voltage between the source and drain, essentially current cannot flow from the source to the drain in the off state, assuming here the gate and source are shorted together. So essentially VGS is equal to 0. Now let's look at the on state. We'll have the same thing. We're going to have a positive voltage difference between the source and drain. Now, instead of applying a zero gate to source voltage, we're going to apply we'll make the source terminal to have a more positive voltage than the gate terminal. So essentially the gate terminal is at a lower potential voltage, lower potential than the source terminal. And why is that the case? If it's at lower potential, it essentially there will be electric fields that basically will pull positive charge from the region that's rich in holes or positive charge, and they will accumulate gradually under the gate or under the silicon dioxide to form the channel. And when VSG S, because the source is higher in voltage than G, and again why the source is higher in potential than the gate instead of having the gate higher in potential than the source, as in the case of the NMOS. Well, in the case of a PMOS transistor, we want the source to be at a higher voltage than the gate, so that we have an electric field that with negative polarity at the gate, so that it pulls the positive charge to underneath the channel from the source terminal. And when VSG exceeds the threshold voltage of the PMOS transistor, okay, what will happen is essentially the transistor will be on. Essentially, we will have enough positive charge accumulated underneath the gate that forms a conducting channel, and so shorts the source or connects the source to the drain. So once VSG is higher than or equal to the threshold voltage of the PMOS transistor, we have enough holes or positive charge in the area underneath or the region underneath the silicon dioxide that forms a conducting channel between the source and drain, and basically current will start to flow from source to the drain due to the positive voltage that's applied. By the way, why I put absolute value? Because while the NMOS transistor threshold voltage is larger than 0, the threshold voltage for the PMOS in data sheets and other documents is less than 0. And the reason is the threshold voltage is referred to VGS. So basically, if I just multiply both sides by negative, then we will have VGS should be less than or equal to VTB negative in order for the transistor to turn on. So I don't like the confusion of the negative polarity of a VTB, or negative sign of the threshold voltage for a PMOS. So I just like to say if VSG is larger than the absolute or equal to the absolute value of the PMOS threshold voltage, then the transistor is going to be on. Otherwise, if VSG is less than the threshold voltage of the PMOS, then there isn't enough holes in the channel or underneath the silicon dioxide or the region underneath the silicon dioxide in the PMOS to form a conducting channel, and so the transistor is going to be in the off state. Now, what is the symbol for the PMOS? Well, if we go back, we said the NMOS can be represented with this symbol, where this is a drain, this is the source, and this is a gate. The PMOS can be represented with the same symbol. We just add a bubble at the gate. So we have gate, source is the terminal that's at higher potential in a PMOS, and then the drain at the bottom. There's also another way to represent the NMOS and PMOS, or simple. So essentially, if this is drain and this is the source, we indicate the source terminal, the terminal that has lower potential, with an arrowhead. The PMOS also has a corresponding symbol, and that's typically the symbol used for designing amplifier. So this is gate, source, and drain, and then the source terminal is represented by an arrow pointing from right to left instead of left to right. And of course, we know the source terminal is the terminal of higher potential. So these are the two symbols for the NMOS and PMOS. Now, let's take a PMOS transistor. And what we are going to do here is we'll connect the source terminal by the highest potential in the circuit, which is VDD. That's something you can try in the lab. And then we're going to connect a positive voltage between the source and drain terminal, so VSD. And we're going to have the gate at a lower potential than the source of VSG is a positive value. And for a specific VSG value, we're going to sweep VSD from 0 all the way to VDD. Remember, the positive terminal of this voltage source is connected here, so when it's 0, it's actually the drain is equal to VDD voltage. And then when VSD is equal to VDD, then the voltage across or at the drain is basically equal to VDD. So as we increase VSD, we'll see that the current, which in this case flows from source to drain, will increase linearly, because essentially the transistor in this state behaves as a resistor. So in this region, the transistor basically behaves as a resistor. And this resistor, as we did for the NMOS, is basically has an equivalent on resistance. In this case, it's P for PMOS. That's equal to 1 over Kp multiplied VSG minus the threshold voltage of the PMOS transistor. We will talk about what is the Kp, but essentially it is the complementary value of the Kn. So essentially we have Kn, the NMOS transconductance parameter. Kp is going to be the PMOS transconductance parameter. Okay, so initially for low VSD values, when this source is small in value, 50 millivolt, 10 millivolt, up to 100 millivolt, depending on the technology, essentially we have the drain current increasing linearly with the voltage applied across the transistor, which is the behavior of a resistor. And if we measure the equivalent resistance, which is the slope, or 1 over the slope of this straight line, we'll find essentially it's given by this relation. And as we increase the current, the voltage VSD across the transistor further, we'll find that the current will continue increasing linear until it starts saturating, until we reach VDD. So again, where is it going to saturate? At V over drive. And what is the value of V over drive? The value of V over drive for a PMOS is essentially VSG minus VTP. Okay, so when VSD is larger than V over drive, which is the VSG minus VTP, essentially the transistor current becomes constant, and essentially the transistor enters the saturation region. And essentially, when you have a constant current versus the voltage across the elements, that's the behavior of a current source. Okay, so here a deep triode, where the relation is linear, that's called deep triode region. The transistor behaves as a resistor. In saturation region, the transistor behaves as a current source. So now let's write the relation or the governing law for the transistor. So again, the current for the PMOS ISD will have three parts. The first part is if the VSG is less than the threshold voltage VTP of the transistor, then the current is zero. On the other hand, for the other two equations, we will have VSG is larger than or equal to the threshold voltage of the PMOS. What differentiates them is essentially the source to drain voltage. If the source to drain voltage is basically larger than V over drive, the transistor is in the saturation region. If VSD is less than V over drive, the transistor is basically in the triode region. Sat region and triode region. In the saturation region, this current, as we mentioned for the NMOS, the transistor behaves also in a PMOS, the transistor also behaves as a voltage controlled current source, where the voltage that's controlling that current source is basically the VSG voltage source. And so its current is given by the relation Kp divided by 2 times V over drive square, where V over drive is given by this expression for the PMOS. And Kp, by the way, is called essentially the PMOS transconductance parameter, and it's equal to Kp bar multiplied by the width of the PMOS and divided by the length of the PMOS, where Kp bar is the process transconductance parameter for the PMOS. And now if we compare the Kn, or let's say Kp bars, the process transconductance parameter for a PMOS, to that of the transconductance parameter for an NMOS, we'll see that Kp is usually 4 times smaller, or between 4 times smaller and 2 times smaller, essentially. And so for the same width and length, we can expect that the NMOS will provide higher current than a PMOS for the same width and length, the same dimension, channel dimensions. The NMOS transistor is better than a PMOS because it provides a higher amount of current and lower equivalent on resistance, because the Kn is larger than a Kp 4 times to 2 times, depending on the technology. So going back, in the saturation region, the transistor behaves as a voltage controlled current source, and its current is given by this relation. On the other hand, in the triode region, we'll find that the transistor current is given by, let's extend this trace to here. Essentially, we have Kp multiplied by V over drive VSD minus VSD squared divided by 2. Just like for an NMOS, but here we just reverse the polarity of the voltage. Instead of VDS, VSD, instead of VGS, VSG. And of course, we take the absolute in V over drive, we take the absolute value of the threshold voltage, the PMOS threshold voltage. Okay, so these are the corresponding three expressions for the source to drain current in a PMOS. Now, one last thing to mention about NMOS and PMOS currents versus voltages relations. So we saw the relation between current, drain current, in both PMOS or NMOS versus VDS or VSD. Essentially, it starts linearly increasing and then it saturates to a constant value, right? That's the current essentially versus. So again, the drain current with respect to the voltage difference across the transistor terminal drain and source. For in a PMOS or NMOS, both have this behavior. It increases linear and then saturates. On the other hand, if we plot this characteristic instead of versus VSD or VDS in an NMOS, we sketch this relation for an NMOS or PMOS, the current, whether it's I just call it ID, but this mean in a PMOS, I mean it's going to be I source to drain. In an NMOS, it's going to be I drain to source. Okay, so ID versus VGS or VSG. So in a PMOS is going to be VSG. In an NMOS is going to be VGS. We have the threshold voltage VT. For a PMOS it will be VTP. For an NMOS it will be VTN. Or so is absolute value of VTP. For an NMOS it's going to be VTN. So we said below when the VSG or VGS is less than the threshold voltage of the transistor current, drain current is going to be zero. And once we exceed that, it conducts, right? And essentially, we found that particularly in the in saturation region, if we are plotting this curve or this sketch for the saturation region for either of the PMOS or NMOS, so essentially this is a V overdrive. And so we are just interested in the saturation current for different gate to source voltages. We'll find that it's given by the relation for a PMOS is given by Kp divided by 2 V overdrive square. For an NMOS is given by Kn over 2 V overdrive square, where V overdrive is basically in an NMOS is VGS minus VT square. For a essentially PMOS is going to be VSG minus VTP square, and let's call this VTN. So this is basically the equation for y equal to x minus a square, right? Whatever constant outside b, whatever. And this is basically the the relation for a quadratic curve with centered around point A, x equal to a. And so basically it will be like this. But since the transistor, we can't, if we sketch this relation, it will be like quadratic curve around VT. But we know that when the VSG or VGS is less than 0, the current is 0, so it will be 0 here. And then it's quadratically increases with VSG or VGS as we increase these gate to source voltage. And of course, again, this is only, here I'm drawing the drain current when both transistors are in saturation, whether it's NMOS or PMOS. Let's see how to express the VGS across a transistor in terms of the current flowing into the transistor. Let's see the solution for the NMOS case and for the PMOS case. For the NMOS case, let's assume this is the NMOS transistor that we have. This is the source terminal. This is the ground. And essentially we want to find the VGS as a function of the current that's flowing from the drain to source. Let's call it ID. So we are given the value for the current ID, say 10 milliamp, 100 milliamp, and we need to find what is the value of the corresponding value of VGS. Well, and assuming, of course, in both cases, the MOSFET is operating in the saturation region. So in saturation region, we know that the current of the transistor ID is going to be for an NMOS Kn divided by 2 VGS minus VTN square. So if we multiply both sides by 2 ID over 2 by Kn, times ID in the left side, we get VGS minus VTN square on the right side. If we take square root of both sides, we will have plus minus square root 2ID divided by Kn is going to be equal to VGS minus VTN. And so VGS, the corresponding value, or the value of VGS for this particular ID flowing in the NMOS transistor while it's in the saturation range or region, saturation region, so is going to be VTN plus minus square root 2ID divided by Kn. Now we have two solutions. Which solution should we select, the positive solution or the negative solution? Well, if we select the negative solution, this means VGS value is going to be less than VTN. So if we select the negative solution, this is going to mean that the gate to source voltage of the transistor is lower than its threshold voltage, which means it's off. So that's not valid. So the solution, the only valid solution is the positive solution, VTN plus square root 2ID over Kn, which is given by this equation. For the PMOS transistor, let's assume this is a PMOS transistor. We have a specific ID current flowing from source to drain, and we need to find the corresponding VSG that will produce this current. So say this current is 5 milliamp, 50 milliamp, and we need to find the corresponding VSG. Assuming the transistor, the PMOS, is in the saturation region, so we'll start again that ID, this current, is going to be equal to Kp divided by 2 VSG minus VTP absolute value square. And if we do the same math that I did on this side, we'll end up with the fact that VSG is going to be equal to VTP plus or minus square root 2ID divided by Kp. Again, we're going to select the positive solution because the negative solution means that the VSG is lower than the threshold voltage, which means the transistor is off, which doesn't or contradicts essentially the initial assumption that or was given in the problem as the transistor is conducting a current equal to ID. And so in this case, V is the corresponding VSG for a particular ID is given by this equation. Now, a second point or a second observation about the saturation region of a MOSFET, we said that for an NMOS, the condition for an NMOS to be in the saturation, this is the source, drain, and this is the gate of the transistor. And the voltage VDS should be larger than or equal to VGS minus VTN, or essentially larger than or equal to the overdrive voltage. Now, if we expand this as VD, the drain voltage, minus the source voltage is larger than or equal to the gate voltage minus the source voltage minus VTN, we can cancel VS with VS. And so we end up with the fact that and if we subtract let's move VTN to the other side, so we have VTN plus VD is larger than or equal to VG, and then we can subtract VD from both sides, and we end up with the fact that VG minus VD is going to be less than or equal to VTN, or basically VGD is less than or equal to VTN. So basically this means that the drain voltage for the transistor to be in saturation, if this is the gate voltage value, assuming it's measured from the ground, the drain voltage, in worst case, it can't go one threshold voltage below, the gate voltage, the drain voltage cannot go one threshold voltage drop below the gate voltage. It has to be higher than this value, So VGD essentially should be less than VTN. So this is the minimum value. Any value larger than that for the drain voltage is acceptable for the transistor to be in saturation. And the same thing if we have a PMOS and gate. And we said that for this transistor, for the PMOS to be in saturation, its source to drain voltage should be larger than or equal to the overdrive voltage, which is VSG minus VTP, absolute value. Again, if we cancel S with S, and then we multiply both sides by minus sign, so we'll have VD is less than or equal to VG plus VTP, and then we can move or subtract the gate voltage from both sides, so we have VDG is going to be less than or equal to VTP. So basically the condition for saturation is that the drain to gate voltage must be less than one threshold voltage drop. All right. What's an amplifier circuit? An amplifier circuit is basically a circuit that provides power gain. So essentially, it takes as an input a given, say, signal with a specific amount of power, say Pn, and produces an output signal that's almost identical, but with a much larger power into it than the. So why we need this type of circuits? Well, imagine someone is speaking in a room that contains say 500 students or 500 audience. So in that case, without using the microphone, no one will be able to hear that individual. However, if we to make him or to make his voice audible to all the all the people attending the lecture or essentially the talk of that individual, we need to use a sound system. So we have a microphone. In this microphone, the individual speaks. Say the microphone terminal is connected to ground and the other terminal. And then this microphone will take the mechanical waves produced by the sound of the speaker, the individual is speaking, and convert it into corresponding electrical signal. And this electrical signal is very weak. So we take an amplifier. This amplifier produces the same shape of signal, but with a much larger amount of power in it, so that it can drive a loudspeaker. And this loudspeaker is going to take this P out, convert it back to mechanical or vibration energy in order to be, or essentially sound, so that everyone be able to hear that individual. So if this individual, say, produces an output power, say 1 milliwatt, the amplifier is going to take this signal, produce an output signal that's replica of the input signal, but with a much larger amount of power. So the input power here, say the microphone is lossless, so it will take the 1 milliwatt mechanical energy converted into 1 milliwatt electrical energy or electrical power, sorry, and then the amplifier will amplify this signal, say 100 times or 1,000 times, so it will produce a 1 watt. So the output signal is a replica of the input signal, but with a much larger amount of power into it. And then the speaker, assuming it's lossless, will take the 1 watt electrical power and convert it into 1 watt of mechanical voice power. Okay, so everyone will essentially will be able to hear the speaker, because their voice essentially is amplified 1,000 times louder. Okay, so what's an amplifier again? It's a circuit that provides power gain, produces an output signal that's a replica of the input signal, but with a much larger amount of power into it. So one question is, where does the amplifier take or generate this extra amount of power? The input power is 1 milliwatt, the output is 1 watt. So where did the 99 milliwatt came from? Well, it came from the DC supply of the amplifier, VDD of the amplifier. That's essentially what provides the remaining amount of power. Okay. To be able to create an amplifier circuit, we need a voltage controlled current source. And why is that the case? So in the sound system we mentioned, we will have a microphone. This microphone connects to an amplifier. The amplifier essentially will take, say, the very low input power coming from the microphone and amplify it, add power to it from the input DC supply, and create, say, 1 watt output, and then it will go into the speaker. Let's say the other terminal is connected to VDD as well of the speaker. Now, why we need a voltage controlled current source to be able to build an amplifier? Well, as we mentioned, an amplifier is basically a circuit that is able to provide power gain, or specifically a circuit that replicates the weak input signal that has low power, say 1 milliwatt. It can replicate this input power at the output and create the same replica but with a much higher output power into it. And in this way you will be able to hear the voice of the speaker in a large room. Alright, so what is the secret of the amplifier, or what's the secret behind the circuit being able to provide power gain? Is its ability to operate as a voltage controlled current source. Why? Well, let's assume that the microphone, we can model it as a current source in parallel with a resistor, and let's call this resistor R. And then we are going to use a voltage controlled current source to take this signal, or the signal produced by the microphone controls the current of the voltage controlled current source. Now, the current produced in the voltage controlled current source is given by Gm times Vn. And so the produced current, let's call it I out, or let's call it ID. So the produced current ID will be equal to Gm times Vn. Vn is essentially the voltage difference between this node and the ground node, which basically, say if the microphone is producing a current I, this voltage will be I times R. Now, if we divide both sides by I, so ID over I is equal to Gm times R. Let's assume for simplicity that Gm is equal to 1 milliamp per volts, the transconductance of the voltage controlled current source. And let's assume the resistance R, which is the equivalent output resistance of the microphone, is equal to, say, 100 kilo ohm. So the ratio between the current produced, and by the way, the current that's produced in by the voltage controlled current source is a replica of the current in the microphone, right? So if the current of the microphone is, say, some random signal like this current that's produced by the voltage controlled current source will be an exact replica, but it's going to be a much larger version. Okay, like let's say, okay, so it will be much larger, say 100 times larger. How? If we divide ID and I, if we look at this ratio, is given by Gm times R, which is equal to, if we multiply these together, is 100 times. So basically, we are able, when we use a voltage controlled current source, we are able to replicate the input signal and the input current signal, which is the signal produced by the microphone, and increase its magnitude 100 times. And what does that mean? Well, assume that the equivalent resistance of the loudspeaker is also R. Okay, say this is the ground. Let's connect this terminal to the ground. So this means that essentially the power that will produced in the speaker, the speaker is represented just by a resistor, so the output power P out will be essentially the current produced by the voltage controlled current source times the equivalent resistance of the loudspeaker. And here I'm assuming that the equivalent resistance of the loudspeaker is equal to the equivalent output resistance of the microphone model in the microphone model, just for simplicity. And so basically the input power which is I square, the input power produced by the microphone, which is I square times the resistance, the equivalent resistance of the microphone is R times R. So essentially, if we look, since we amplify the input current of the microphone 100 times, we'll find that the output power is going to be 10 to the power 4 times the input power. Okay, and the whole secret is when we use the voltage controlled current source, it produces an identical replica of the input current signal but amplified in magnitude 100 times. So if we multiply it by the same resistance of the microphone essentially, or we assume the loudspeaker equivalent resistance is equal to the output resistance of the microphone, then the output power will be 10 to the power 4 times the input power. Okay, so my point here is the secret behind a circuit being able to provide power gain is its ability to work as a voltage controlled current source. So it takes the small signal amplified 100 times or whatever times the current gain it provides, and then we multiply that by the equivalent load resistance, and we get essentially the output voltage signal that will be applied to the speaker, by the way. So if V out, if we look at V out, which is the voltage that will be applied across the speaker, is going to be the output current ID multiplied by the equivalent resistance of the speaker R. ID, as we said, is going to be GM times the resistance R times the current, the input current I, and another R. So essentially is going to be GM R squared times I. But hey, once we use the voltage controlled current source, we will be able to replicate the input current signal 100 and amplify it in magnitude 100 times, and so essentially increases output power by 10 to the power 4, assuming the loudspeaker equivalent resistance is equal to the output resistance of the microphone. Now, let's take this simple circuit and actually implement it. Here I used a voltage controlled current source, and I mentioned that previously when I described the NMOS and PMOS operation, that the NMOS transistor in the saturation region, it essentially behaves as a voltage controlled current source, right? Where this is a drain, this is a source, this is a gate, and its current is given by Kn over 2 V over drive squared. Okay, so luckily we have an element that behaves as a voltage controlled current source. Yeah, of course it's quadratic relation, not linear as in here, so it will not produce an identical replica. The output signal will be, output current is going to be a little bit distorted, but we're going to use something called small signal operation, and we will discuss that in a future video. So now my point, the NMOS essentially is behave as a voltage controlled current source. So if we use the NMOS and assume it's operating in saturation, and we assume here the input signal connected here, and let's call it for generally VGS, And then the load resistance is the equivalent load resistance of the speaker. We are going to call it R. And then we're going to connect this resistor to a supply voltage to provide power, because as I mentioned, the voltage controlled current source essentially is not magically generating the power externally. The extra power that's in the output is coming from the input DC supply. So that the total input power that's coming from the microphone plus the DC supply is equal to the output power, assuming lossless operation. Okay, so this acts as a voltage controlled current source, assuming it's in saturation region, and then this is basically the loudspeaker equivalent resistance. And VDD, as we're going to see in the future, essentially behaves as what's called AC ground. So for the AC signal that's produced, which represents as a replica of the actual voice produced from the microphone, which is the useful signals that we need to amplify. Essentially, we'll see the VDD supply as an AC ground, as a ground basically. Okay, but that's something we'll discuss in the future. And let's call this voltage the output voltage, or for simplicity, we'll call it VDS. Technically, the output voltage should be the voltage that's essentially across this resistor, because this is the speaker. However, as I mentioned, as we're going to see in the future, VDD behaves as an AC ground. So for now, just for simple math, we're going to assume the output voltage is the voltage between this node and the ground node, so VDS. Now, something important, and here this is called a common source amplifier. And the reason it's called a common source, because as you can see, the source terminal is connected to the ground, which is a common node between the input and the output. So common source amplifier. To understand the operation of this amplifier in detail, we need to plot what's called a voltage transfer characteristic. And that's basically, we just plot the output, which is VDS, versus the input, which is VGS. So on the x-axis, we have the input, VGS, or sorry, let's call it G capital S capital. So G capital S capital, and VDS on the y-axis. Now, we know that for voltages that are below the threshold voltage of the NMOS, the transistor is going to be open circuit, and so essentially VDS is going to be equal to VDD. Then, once the transistor turns on, once VGS exceeds VTN, the transistor is going to turn on. And it's going to be in the saturation region. And the reason is because once the transistor turns on, its current will be very small, so the voltage drop across this resistor is going to be very tiny. And so essentially this node will be very high, while VGS is very low, assuming the input signal is small in value, or yeah, of course, in here it's very close to VTN. So the input voltage is close to just a little above VTN, while this node, the drain node, is very close to the supply voltage VDD. So it's much higher. So we have a positive voltage from here to here. So the transistor, of course, will be in the saturation. And remember, we said that for the transistor to be in saturation, the gate to drain essentially should be less than VTN. So essentially, in this case, that's satisfied when we have the drain node at a much higher potential than the gate node. So once the transistor enters the saturation, the current in the transistor essentially, as we increase VGS, will increase rapidly. And what we are going to see, since the current increases, quadratically, we'll find that the voltage drop across this resistor will increase quadratically, And so essentially the output voltage is going to decrease quadratically until this point when VDS essentially reaches what's called the overdrive voltage, VGS minus VT. And at that point, essentially, the drain voltage will go below V overdrive, and so the transistor is going to enter the triode region, and its current essentially will increase much slowly as we increase VGS compared to in the saturation region. So here the transistor was in saturation region, here it was in off or cutoff, and now here it enters the triode region. Okay, at this point. And then in the triode region, as we increase VGS further, as I mentioned, the current will increase, but with a less slope essentially. And so essentially we will find that the output voltage will decrease more gracefully until we reach VD, until VGS reaches VDD. So this is just an intuitive description of the operation of this amplifier to be able to sketch its transfer characteristic. But now let's take that and let's analytically find the equation that govern VDS, the output voltage, in the saturation region. So now, since the transistor in the saturation region, its current, as we know, drain current, is given by Kn over 2 V overdrive square. Now, VDS will be basically VDD minus the voltage drop that's across the resistor from KVL. So we have ID times the resistor R. So basically we have VDD minus Kn over 2 times the resistor R V overdrive square. So that's the expression for the output voltage. And as you can see, this curve, if we sketch the voltage transfer characteristics, so we said initially the transistor is off, so VDS is equal to VDD. And then once it connects, we have this equation, which basically is a quadratic curve that's going downward. Like essentially this is a quadratic gradation if we look at it, but starting from VDD, and of course we only take this side, so that's going downward until the transistor enters the triode region when the drain to source voltage becomes equal to the overdrive voltage. Let's call this VOV1, and this happened at VGS1 value, and then it enters the triode region. So this is saturation, this is cutoff, and this is triode. Now what I'm interested in doing right now, I want to find the value of V overdrive 1 or VGS1 minus VTN. So V overdrive 1 is equal to VGS1 minus VTN. Basically, I want to find the value of VGS1 at which the transistor will enter the triode region. So we can replace VDS by V overdrive 1 because at this point VDS is equal to V overdrive 1. And then we have VDD minus Kn over 2 times R. and then here we have v over drive 1 square. So if we bring this term to the other side, we have kn over 2 times an r in here, v over drive 1 square plus v over 1 minus vdd equal to 0. And of course you can use a relation that v over the solution will be minus b plus minus square root b square minus 4ac divided by 2a, where this is a, b is 1, and c is equal to minus vdd. And if we do the math, we'll find that v over drive is basically equal to square root 2kn times the resistor R VDD plus 1 and then minus 1 divided by kn times the resistor R. Okay, and from here essentially we can find the value of VGS1 by replacing VGS1 is equal to whatever this value plus VTN. Right. So this is essentially V over drive 1, just add to it VTN, and this is going to be the VGS1 value at which, the input voltage value at which the transistor starts entering the triode region. One important point here that I would like to clarify is that in this region, in the saturation region, is the region where we use the transistor to amplify the input signal, and that's something I mentioned before. And we said that in order to be able, the secret for a circuit to be able to provide power gain and act as an amplifier circuit is its ability to operate as a voltage controlled current source. And we said the NMOS in the saturation operate as a voltage controlled current source, and so it can build an amplifier. And as you can see in the saturation region, if this is the output voltage and this is the input voltage, if it's an amplifier, the output voltage should be larger in magnitude. It should be a replica of the input, but it should be larger in magnitude than the input so that it has higher amount of power. And as you can see, the slope of the relation between the output and input in the saturation region is essentially higher than 1. And this means at this point, in this particular point, if we measure the slope, we'll find that the relation between VDS over VGS, which is the input output to input ratio, is larger than 1, and this means essentially indeed the output is larger than in magnitude than the input if, say, the input signal is somehow changing around this point. So we'll find that the output signal is changing with the same with a larger magnitude.